Today I'm going to talk about the submicroscopic world and what we know about atoms. So at the heart of most of what we're going to discuss in chemistry are atoms, and atoms are the smallest fundamental units of matter that we know. And sometimes they're joined together to make molecules. But I want to just give you an idea of how small they are relative to other things. So we have this scale here on the right, and you can see the Earth and our atmosphere. Those sorts of things are astronomical in scale. And then macroscopic things are things that we can see with the naked eye. So that's a lot of different things, all the way down to like a grain of salt. So that would be one of the smallest macroscopic objects. Microscopic things are things that we need a microscope to see. All right, and then even smaller than that are submicroscopic particles, which would include things like molecules and atoms. Even larger molecules like proteins fall into the submicroscopic category. Right, now the idea of the atom actually came about over 2,000 years ago, and there were two main theories at the time for what matter was made of. The first was Aristotle, and I'm sure you've all heard of Aristotle. He was a fairly famous philosopher, and he thought that all materials were made of various proportions of four fundamental qualities, which he called hot, dry, cold, and moist. And that, for example, air is a combination of hot and moist. Fire is hot and dry. Earth would be dry and cold, and water is also cold, but it's moist, not dry. So he thought that these things together gave us some combination of those things could account for all matter on Earth. And his theory gained a lot of traction because he was a pretty famous, pretty well-known philosopher at the time. But it turns out he was wrong. And so the other philosopher is Democritus, and he imagined that atoms were the smallest thing you could get to if you kept cutting something in half over and over and over again. So if you kept cutting iron in half again and again and again, eventually you wouldn't be able to cut it in half anymore without it not being iron anymore. And he called that smallest particle an atom, which comes from atomos, which means indivisible or unable to be cut. So about more than 2,000 years after these original theories came about, there was a French chemist. He was actually just a rich businessman who had an interest in science, Antoine Lavoisier, and he did experiments in his house and actually was able to come up with some of our most important laws. So he first it was the first to introduce the law of conservation of mass, which basically says that we can change water from a liquid to a gas, but the mass still stays the same as long as we don't change it by chemical means. And Lavoisier also hypothesized that an element is any material that is made of fundamental substances that cannot be broken down into anything else. So oxygen would be an example of an element, but water, which Aristotle thought of as an element, isn't actually an element because it can be broken down into hydrogen and oxygen. And that's all based on experiments that Lavoisier did in his home in France. Then building on the experiments of Lavoisier and the original theory from Democritus about the idea of the atom, a English chemist named John Dalton proposed a series of postulates that he thought explained how atoms or matter works. And the first is that each element consists of indivisible, minute particles called atoms. So this draws on that same term that Democritus put forth, but now is based on the experiments that have been done in the 1700s. All right, the second one is that atoms can be neither created nor destroyed in chemical reactions. Okay, so if you're doing a chemical reaction and you start with oxygen, even if it's bound to one thing or another, it's still going to be oxygen at the end. It just might be in a different form. All right, the third is that all atoms of a given element are identical. We now know that this isn't completely true, but we'll get to that in a little bit when we get to subatomic particles. But for our purposes, all atoms of a given element do have the same properties, okay? And then the fourth is that atoms of different elements have different masses. So if you have two different elements, their masses cannot be the same. If they're the same, then they would be the same element. Okay, so these are four fairly basic postulates, which are just claims that he assumed to be true, and they're all based on experiments that had been done at that time. All right, and then the last chemist I'm going to talk to you about today is Dmitry Mendeleev, and he was a Russian chemist, and he wanted to, along with a lot of other people at that time, was trying to organize the elements into some format that made sense rather than just being a random list of elements. And so at this time, a lot of the elements were known, not all of them, but many of them were known, and their atomic masses had been measured. And so he thought about ordering them by atomic mass, and he also thought about grouping them based on their reactivities, so the properties that they have in common and what things they react with or don't react with. And so that is how he put the groupings together, and he spent a lot of time organizing and reorganizing, and the story is that he in a dream, had this vision of a table, and when he woke up, he was able to assemble the elements into what is similar to our modern periodic table. Here, it's more vertical, whereas ours is horizontal. So what he ended up doing was really powerful for a couple of reasons. One, the most important one, is that it actually made predictions about elements that hadn't yet been discovered. So there were a couple of holes in his organization, and he made claims about the gaps being places where elements would go after they had been discovered, and even made predictions about what their properties would be, what their approximate masses would be, and it turns out that we now know he was right, and those elements that hadn't yet been discovered were later discovered and fit right in where he suggested they would. So his discovery was so important that this is still the periodic table we use today and will probably always use, and they keep adding on to it as new elements are created or discovered, but we can already tell basically what their properties will be based on the organization of the table.